Assalamu alaikum and welcome to lecture 2 of CS218 Data Structures and Algorithms. In the last lecture, we learned about the algorithm, we learned about abstraction and its types, we explored the abstract data type in detail, we were introduced to the idea of a data structure, we explored the operations performed on a data structure, and we were introduced to different kinds of data structures. We now begin our work with analysis of algorithms. We are going to use book 1 chapter 4 and book 2 chapter 2 for this topic. So we touched algorithms in the previous lecture as well, and I pick the topic up from the same point. An algorithm is a sequence of clear and precise step-by-step instructions for solving a problem in a finite amount of time. If you remember, this is the definition that I gave you in the previous lecture. An algorithm is a well-defined computational procedure that takes some values as input and produces some values as output in finite time. Algorithm plus data is a program. So what is pseudocode? Pseudocode is plain language description of the steps in an algorithm. Pseudocode often uses structural conventions of a normal programming language, but it is intended for human reading rather than machine reading. It typically omits details that are essential for machine understanding of the algorithm, such as variable declarations and language-specific code. In the pseudocode, the programming language is augmented with natural language description details, where convenient, or with compact mathematical notation. The purpose of using pseudocode is that it is easier for people to understand than conventional programming language code. So why do we analyze algorithms? Once an algorithm is given for a problem and decided somehow to be correct, an important step is to determine how much in the way of resources such as time or space the algorithm will require. An algorithm that solves a problem but requires a year is hardly of any use. Likewise, an algorithm that requires thousands of gigabytes of main memory is not useful on most machines. Analyzing an algorithm means predicting the resources it requires. These resources may be memory, communication bandwidth, computer hardware, and computational time. We mostly analyze algorithms for memory or time. We are always interested in knowing if our algorithm is faster than others like it. We are always interested in knowing if our algorithm takes less memory to compute than others like it. So most of our analyses are either time analyses or memory analyses. How to analyze algorithms? There are two ways of analyzing algorithms. One is called empirical analysis and the other is called theoretical analysis. So let us talk first about empirical analysis. Empirical analysis is done by coding the algorithm in a high-level language and running it on a computer over a suitable large range of inputs. The results of empirical analysis are highly dependent on the chosen high-level language, the machine on which the algorithm is run, and the inputs that are provided. Problems with empirical analysis. You must code all algorithms, though you will finally keep only one of them and discard the rest. So you will have to spend time and money for the programming of algorithms, all but one of which you will discard. A slow algorithm may perform better than a fast one if it is written by a better programmer. This means that the programmer's skill will influence the results of the analysis. If all algorithms are programmed by the same person, even then the programmer might like one algorithm more than the others, and this bias may lead him to code this algorithm in a better way, ultimately affecting the results. Results on one set of inputs may be completely different from those for another set of inputs. The results for the applied inputs cannot be assumed to be representative of results of inputs which have not been applied on the algorithm. The inputs chosen to be used may favor one algorithm more than the other, so results will be dependent on the inputs applied. All algorithms under scrutiny must be run on the same software and hardware platforms. Also, results may change drastically if you change the hardware and/or software platforms. You may find that you do not have the budget to implement the better algorithm. Now, even though you know which algorithm is better, you cannot afford to run it. So you must look for another algorithm and start empirical analysis all over again. Let me introduce you to the idea of input size. The input size or data size of an algorithm is the number of data items provided to the algorithm by the calling entity. Input size is denoted by n. Consider the algorithm shown here. A and B are lists of n elements each. The algorithm takes another list C of n elements. Then it takes the ith element of A and the ith element of B, and it adds them together and stores them in the ith element of C. And after all elements are done, it returns the list C. The two lists of length n are being added, so the input size here is twice of n. As empirical analysis is costly and may not lead to a solution, we do not use this analysis for algorithm. Instead, we use theoretical analysis. Theoretical analysis uses pseudocode for the algorithm instead of programming code. So we do not need to spend anything to get the algorithm coded. Theoretical analysis characterizes running time as a function of the input size n. Suppose you are asked to read 10 pages and you take 7 minutes to read them. Now if I give you 20 pages to read, is it safe to assume that you will take more than 7 minutes to read them? What does this show? When the input size increases, the running time of the algorithm also increases. I can say that the running time of the algorithm is a function of the input size. Theoretical analysis takes all possible inputs into account. This removes the probability that results may be representative of the applied input set only. Theoretical analysis evaluates the algorithm independent of the hardware and software. This happens because we never code the algorithm, so it never runs on a machine. All analysis is done on paper. So what actually happens in theoretical analysis? In theoretical analysis, we count the primitive operations that an algorithm performs for input size n. A primitive or elementary operation is defined as a high-level operation that is largely independent of the programming platform, input data, and the algorithm used. Following is a list of primitive operations. Performing an arithmetic operation, for example, adding two numbers, comparing two numbers, assigning a value to an identifier or a variable, indexing into a list or following a pointer reference, calling a method or function, returning from a method or function. Now that you know what primitive operations are, I ask you to count primitive operations for the algorithm shown here. This algorithm computes the sum of the list A containing n elements. So when it starts, it puts the 0th element of A in a variable known as sum. Then it runs a for loop from 1 to n minus 1. And every time we enter the for loop, it takes the ith element of A and adds it to the value of sum. When the for loop ends, the algorithm returns sum. The first thing that I have done over here is that I have labeled each line with a number, and that will make it easier for me to refer to it during the analysis. What am I interested in? I am interested in the number of operations that take place in each line of the algorithm. Look at line number 1. What are we doing here? We access the 0th element of A. This is one primitive operation, and then we assign this value to the sum variable. This is another primitive operation. So the number of primitive operations in the first line are 2. Look at line number 2. In line number 2, we have a for loop in which I goes from 1 to n minus 1. Before finding the number of operations in the for loop, let us look at the general structure of any for loop. These are the things that we do in a for loop. First, we initialize the counter variable. Then we check if the value of the counter variable falls within the valid range of the for loop. Then we move into the body of the for loop. Then we update the counter variable. And then we go back to checking the condition. My first question is, how many times do we initialize the loop variable? And your answer would be only once. Look at line number 2. I has been initialized to 1. This happens only once. Once I has been initialized, then it is checked if I falls within the valid range for this for loop. What is the valid range for our for loop? Our for loop will go from 1 to n minus 1. So these are valid values of our loop. from 1 to n minus 1, or these are true values of our loop. How many true values do we have for this loop? N minus 1 values from 1 to n minus 1. Each time that you find that the value is true, you move into the body of the loop. In our case, the body of the loop is line number 3. When you move out of the body of the loop, you update the counter variable. Usually you increment it, but if you have a step value, then you add the step value to the counter variable. In the end, you come to a point where the condition becomes false, or the value of the counter variable falls out of the valid range. In our case, the value will fall out of the valid range when I becomes equal to n. How many false values will we check for our for loop? Just one. When we will find that the value of I has become n, we will move out of the for. So my question is, how many times do you update the counter variable? The answer is, you update the counter variable for as many times as the true values of the for loop. For our for loop in line number 2, we will update the counter variable n minus 1 times. My next question is, how many times will I check whether the value of the counter variable is valid or not? I will check the condition as many times as the true values plus one false value. I have n minus 1 true values plus one false value. So I will check the condition n times. Number of operations in the for loop are the number of initializations plus the number of times the condition is checked plus the number of times the update is made. And here you are. The first one is the number of initializations. The second term n is the number of times we check the validity of the value of I. And the last two terms, n minus 1, is the number of times the update is made to our counter variable. 1 plus n minus 1, this will become 2n. Look at line number 3. What are we doing here? First we access the ith element of A. Then we add it to sum. Then we assign this result to sum. So these are three operations. And this is the body of the loop. It will execute as many times as the true values of the loop. We have n minus 1 true values. So the number of operations in line number 3 will be 3 into n minus 1. In line number 4, we return the value of sum, which is just one primitive operation. Now I ask you for the total primitive operations. Add all of these and you get 5n. Look at this equation. Running time of this algorithm is 5n. When you increase n, the running time will increase also. Cases for theoretical analysis. When we analyze an algorithm theoretically, we can choose to do so in three ways: best case analysis, worst case analysis, average case analysis. Best case analysis. Provide a set of inputs for which the algorithm takes the shortest possible time or executes the least number of primitive operations. The best case running time of the algorithm is a lower bound on the running time of the algorithm. If Ti is the running time of the algorithm for a set of inputs I and Tb is the best case running time of the algorithm, then Tb is always less than or equal to Ti. Worst case analysis. Provide a set of inputs for which the algorithm takes the longest possible time or executes the greatest number of primitive operations. The worst case running time of the algorithm is an upper bound on the running time of the algorithm. If Ti is the running time of the algorithm for a set of inputs I and Tw is the worst case running time of the algorithm, then Ti is always less than or equal to Tw. Average case analysis. Find the running time of the algorithm for all possible sets of inputs. Find the probability of each input. We assume that an algorithm can be given X different inputs. The running time of input K is Tk and the probability of input K is Pk. The average running time is P1 into T1 plus P2 into T2 plus plus Px into Tx. The average running time is impossible to compute for algorithms with an infinite set of inputs. If T average is the average running time of the algorithm, Tb is the best case running time of the algorithm, and Tw is the worst case running time of the algorithm, then Tb is always less than or equal to T average, which is less than or equal to Tw. In the picture, we show an algorithm with 7 different input sets. For input set A, the algorithm takes 5 milliseconds. For B, it takes 3 milliseconds. For C, it takes 4 milliseconds. For D, it takes 5 milliseconds. For E, it takes 2.5 milliseconds. For F, it takes more than 4 milliseconds. And for G, it takes 3 milliseconds. The best case input is obviously input set E. The worst case input sets are A and D. The average case time would be between the best case time and the worst case time. Which analysis is the most useful? If we know the worst case running time of an algorithm, we can be sure that the algorithm will never exceed this duration for any input that is given to it. The worst case analysis is most useful to a computer scientist. Average case analysis requires a lot of effort because you need to know all the input sets and you need to know the probabilities of all those input sets. So it takes a lot of effort. We only conduct best case analysis when the best case occurs very frequently. Otherwise, there is no use of a best case analysis. Now I ask you to analyze the given algorithm for its best and worst case. The algorithm is called arraymax, takes a list A of n integers and the second argument is the variable n, which shows the length of the list. The output is the maximum element of A. It assigns the 0th element to current max. Then it runs a loop from 1 to n minus 1. If the ith value of A is greater than current max, then the ith value of A is placed in current max. At the end of the for loop, the algorithm returns current max. I label each line with a number so that it is easy for me to talk about these lines. I am interested in the best case analysis. So the first question is, when does best case happen? Line number 1 executes every time. Line number 2 executes every time, and it executes for values of I from 1 to n minus 1. So it executes n minus 1 times. Line number 3 is part of the body of the for loop. So this also executes every time the for loop executes. In line number 3, we have an if. If the condition of the if is true, we move into the body of the if, which is line number 4. But if the condition of the if is false, we skip the body of the if. Line number 5 also always executes. So this means that the best case would happen when, for any input, the condition of the if is always false. This will guarantee that I never move into the body of the if. This is the case when I will do the least number of operations. This is the best case. What kind of input leads to the best case? Consider that you have list A with 4 elements, 17, 15, 9 and 7. When you begin, you put 17 in current max. Then you compare 17 and 15 and the if condition is false. Then you compare 17 with 9 and the if condition is false. Then you compare 17 with 7 and the if condition is false. Notice that in this example, the elements of A are in descending order. So this means that the best case happens when A is sorted in descending order. There is another type of input that will lead to the best case. Suppose that your list contains the same element at all positions. A has 4 elements and A is 5, 5, 5, 5. In this case too, the if condition will always be false. So the other input which will lead to the best case is when all elements of A are equal. I am interested in the number of operations that will happen when the algorithm is presented with best case input. Line number 1 shows that I access the 0th element of A and assign it to current max. These are 2 operations. In line number 2, I have a for loop. There is one initialization in the for loop. True values of the for loop go from 1 to n minus 1. So there are n minus 1 true values. The condition of the for loop is checked for true values plus 1 false value. So the condition is checked n minus 1 plus 1, that is n times. The loop counter is updated as many times as the true values. Updation happens n minus 1 times. So the number of operations for the for loop are 2n. Line number 3 is in the body of the for loop. In line number 3, I access the ith element and compare it with current max. These are 2 operations, and this body iterates as many times as the true values of for. There are n minus 1 true values. So line number 3 executes 2 into n minus 1 times. But since this is the best case, the if condition is always false. And the number of operations in line number 4 is 0 because we never move to line number 4. In line number 5, I return the value of current max. So the number of operations in line number 5 is 1. Total primitive operations are 4n plus 1. Tn is equal to 4n plus 1. Now let us do the worst case analysis. Again, line 1 will always execute. The for loop in line 2 will always execute. The if condition in line 3 will always be checked. If the condition is true, we will move to line 4. Otherwise, we will skip line 4. The worst case happens when the if condition is always true. I have to do the greatest number of operations because every time I have to move to line number 4. What kind of input leads to worst case? Consider that your list is sorted in ascending order. A is 7, 9, 15, 17. So when you begin, you put 7 in current max. But when you compare 7 with 9, 9 is larger. So you put 9 in current max. But when you compare 9 with 15, 15 is larger. So then you put 15 in current max. Finally, when you compare 15 and 17, 17 is larger. So you put 17 in current max. So the worst case happens when the list A is sorted in ascending order. I am interested in the number of operations that take place when the algorithm is presented the worst case input. Again, in line number 1, I do 2 operations, accessing the 0th element and assigning it to current max. In line number 2, I do 1 initialization, n condition checks and n minus 1 updations. Total number of operations is 2n. In line number 3, I do an access to the ith element and I compare it with current max. And this line executes as many times as the true values of the for loop. So the total number of operations in line number 3 is 2 into n minus 1. Every time the if condition is true and every time I have to move to line number 4. In line number 4, I access the ith element of A and assign it to current max. These are 2 operations and this is placed in the body of the for. So it will iterate as many times as the true values of the for. Line number 4 executes n minus 1 times. Total number of operations are 2 into n minus 1. The last line returns one value, which is one operation. Total primitive operations are 6n minus 1. Tn is 6n minus 1. Let us see another algorithm that computes the sum of list A containing n elements. We are asked to find the worst case and the best case. If you look at the algorithm, you will see that no matter what kind of list you provide to this algorithm, every line will always execute. There is no if condition here. So we can say that this algorithm does not have separate worst case and best case, because every line will always execute no matter what is input or what kind of list is given to the algorithm. Now we come to the task for this lecture. Analyze the algorithm for its best and worst cases. Find equations for Tn in both cases. Show all steps. You may do this on paper or you may type your answer. This algorithm called real roots a, b, c computes the real roots of a quadratic equation. It first assigns d to be b square minus 4ac. If d is greater than or equal to 0, it assigns a value in R0 and then another in R1, and then it returns this two-element list R. Save your snapshot PDF or doc as my roll number lec2. If your roll number is 500, the file should be named 500 lec2. Submit your response in the assignment titled Lecture 2 Tasks in Google Classroom. So what did we learn today? We differentiated between the algorithm and the pseudocode. We learned how to do empirical analysis of algorithms. We discussed the disadvantages of empirical analysis. We learned how to do theoretical analysis of algorithms. We were introduced to primitive operations. We discussed best, average, and worst cases of algorithms. And we analyzed algorithms for the first time. Hooray! I leave you with 4 things to do. Read the book, submit your answer to the task in this lecture, note your questions and put them up in the relevant online session, and email your suggestions on content or quality of this lecture at urujain@naduet.edu.pk. Take care. Allah Hafiz.